So we're going to talk about Newton's law of cooling. And again, this is something that comes up quite often in science. So let's take a look at this. So yeah, I can talk. Newton's law of cooling says the rate of change of a temperature of an object is proportional to the difference between the temperature of the object and the temperature of its surroundings. So the first thing that stands out to me, and probably because it's underlined, is difference. So I know that the rate of change of an object, so dy dt, is proportional to the difference between the temperature of the object. So I could write that as, it's got this constant of proportionality, this k, and it's proportional to the difference of the temperature of the object minus the temperature of its surroundings. So we can just maybe say S there. So we look at it's proportional to the temperature of the object minus the temperature of its surroundings. So that's what that told us, was to write this with some calculus because it's talking about rate of change. And now we have to figure out how to solve a problem from here. So the problem, you can read it. There's a metal figurine. It's heated to 150 degrees. Then it's brought to room temperature, or into a room that has 72 degrees Fahrenheit. And it tells us how fast it cools and asks how long will it take for the figurine to reach a temperature of 100 degrees Fahrenheit. So this is our final question. How long will it take for the figurine to reach a temperature of 100 degrees Fahrenheit? So in the end, our answer will be time of some sort, okay? So keep that in mind as we're finding different variables throughout this. Eventually what we're ending up in, what we're trying to settle in, is time, okay? So y is the temperature, which we already used it right here. Y is the temperature, and then minus the surrounding temperature is our proportional relationship. Okay, so here we have this metal figurine. It's heated to 150 degrees Fahrenheit. So the first thing we want to do is try to write a relationship between some of the rate of change and these variables. And we're going to use differential equations to solve that, because why wouldn't we? We're in calculus, right? So what is the temperature of the surroundings? Well, we see here it comes into a room that is 72 degrees Fahrenheit. So the temperature of our surroundings is 72 in this case. So we're going to start there. Now we're going to go ahead and separate the variables and find an actual equation that we can use that doesn't have a derivative in it anymore. So we're going to have dy over y minus 72 equals k dt, because I just, divided and multiplied. Okay, and then we're going to integrate both sides. And the integral of 1 over y minus 72 is ln of absolute value of y minus 72. And that equals kt plus c, remember, because the derivative with respect to t. And then we want to get this y all by itself, so we can get, what we're trying to do is we're trying to get an equation that when we input time, we get out a temperature. Okay, that's all we're trying to do, right? We're trying to input time, get out a temperature. So when we're trying to input a t, we're trying to get out a y. Therefore, y has to be by itself, right? Y has to be completely by itself, so that when we input t or temperature, it's going to spit out a y. Okay, so to undo this, we're going to raise that e to both sides. We're going to end up with y minus 72, and this is e to the kt times e to the c, if you remember the last video. And e to the c is just c, so y minus 72 equals c e to the kt. And then we're going to add 72 to both sides, so we get y equals c e to the kt plus 72. So this is our proportional relationship, or our exponential growth relationship or decay or however you want to call it, cooling. We're calling this Newton's law of cooling. This is our relationship. And so if I put in a t, I get out a y, right? This is my t is my input here and y is my output. But the problem is I have these two extra variables. I have this initial and I have this k that I don't know either one of those. I don't know either of those right now, so I have to find those first before I can just start plugging in time and getting out temperature, because that's my goal, but I can't do it yet. So let's see what we're going to have to do to be able to do that. So the first thing we're going to look for is the first thing we're going to try to find is we're trying to find the C. So first, find C, because we don't know that, okay? So we know that at time equals 0, temperature equals 150 degrees, right? So if we look at this as kind of a coordinate point, at time equals 0, temperature equals 150 degrees, okay? So we can just go ahead and plug that in. We have 150 equals E times 0T at, not T, 0K plus 72. So at time 0, we just plug that in. We have 150 degrees. So we have 150 minus 72 equals C times 1, because E to the 0 is 1. So our initial C is going to be 78 in this case. Okay, so now we've made just a little bit of progress, because now we can write this as Y equals 78 E to the KT plus 72. So we're almost to that point of being able to just plug in a time and get out a temperature, right? But we still don't know how exactly they're proportionally related, because we don't have the constant of proportionality. So that's the K. So that's what we need to do now. We need to find K. So to do that, so first we found C. Now we're going to use 15 and 120. So this, again, this is time and temperature to solve for K. So if we come up here, we look that in 15 minutes, it went from 150 to 120. So at 15 minutes, if we put in time 15, we get out temperature 120. We know that. So we should be able to solve for K now, because then it would be our only variable left, right? We plugged in every other variable. So we know at time equals 15, we get out 120. So our output is 120, 78 E to the 15K plus 72. So we subtract 72 from both sides, and we get 48 equals 78 E to the 15K. Divide by 78, and we get 48/78 equals E to the 15K. Now to undo that, we need to take the ln of both sides, and we end up with ln of 48/78 equals 15K. Divide by 15, and we have ln of 48/78 over 15 equals K. Now again, what you're going to do is you're going to go into your calculator and you're going to push store. Once you find that, once you calculate ln of 48/78 divided by 15, you're going to store that number so that we can use it again. And it comes out to negative 0.323. is what we end up with. Okay, so we've stored that number as K, and now we have finally done all of the legwork that feels like we should be done by now. But you know calculus, we're not done yet. We've done all the legwork so that we can get to this place where we have an equation that if I put in a time, I get out a temperature. So I have 78 e to the, and we're just going to put k in there, kt plus 72. This is our equation. We've solved for c, we've solved for k. Now, if I put in a time, it will spit out a temperature. So we can put in, what do we know? We want to know at what time am I going to get 100 degrees. So I'm actually going to have 100 as my time, not as my time, as my temperature. So I'm going to use T and 100. I'm going to say what time is going to give me the temperature 100. Okay. So I'm going to put 100 in here because that's my final temperature. And I'm saying what time would I have to plug in here to get out 100. So I subtract 72 from both sides. I get 28 equals 78 e to the kt. So that it's 28 over 78 equals e to the kt. And then I'm going to do ln of both sides. So I end up with ln of 28 over 78 equals k times t. And then I just divide both sides by k. I'm putting a box around it because I'm reminding you that it's not actually a variable anymore. It's a number that we've stored in our calculator. So in the end, our time equals ln of 28 over 78, all divided by k, our constant of proportionality, and we end up with time equals about 32 minutes. So it'll take 32 minutes for it to get to 100 degrees. So I know that felt like a lot. I mean, look at that. That is really a lot that we got there, but it's kind of cool, the slow progression of going from, okay, here's our differential equation into our general formula, and then taking this general formula and putting what we know about our current situation in there and finding each constant that we didn't know until we can finally solve it.